by factoring, because for 3, 3, they said solve it by factoring. Now, do both of these have a greatest common factor? Is there something that both of them have? They don't have a number, but do they both have a variable? So we could factor this in out. N factored out of n squared is just n. N factored out of 6n is 6. So we get n times n minus 6. Any two things that multiply together, one of them must be 0. So we're saying either n is equal to 0 or n minus 6 is 0. There's one of our answers. Now for the other one, we have to add 6 to both sides, telling us n is equal to. So our answers are 0 and 6. 31 from 3.3. Because again, when we factor, the first thing we look for is the greatest common factor.
Wait, so that n squared has nothing to do with it?
Because n squared is n times n. And 6n. Both of them do have a common factor of n we can pull out. Normally we don't factor it out because we're normally looking at something like n squared minus 6n plus 5. It doesn't have it. Here, because we didn't have the 5, we can pull that factor of n out.
Okay, I was just wondering.
And that's it. Any other questions on any of the assignments? Okay. All right. So the first thing we want to look at is finding a number. When multiplied by itself, we get a negative. So does anybody come up with an example that would work?
-9.
Times? Guys, -9. That's going to be positive 81, yes?
Yes, sir.
Okay, so that didn't work. Is there another one that could? Well, no, guys. Guys, Logan just screwed up a few. We're going to split that group up. Tyler, you're up here. No, I'm just.
It was literally.
Yep, no, I'm just, okay. But again, now, is there a number that works? Well, no, because a positive times a positive is always positive. A negative times a negative is still a positive. So I'm going to pick, just say I, because really what we're looking for is I squared. I times itself, and we'll say is equal to -1. That's really what we're trying to ask with this question. Something times itself that gives us a negative number. Well, if we solve this, we can take the square root of both sides. So really what we're saying is our number is going to end up equaling the square root of -1, which doesn't exist. So what we end up here is this here. I, our imaginary number, is the square root of -1. Mm-hmm.
What the heck is that weird?
I. And by definition, because again, we give it this kind of curly tail to signify that this is our imaginary number I. And by definition, I is the square root of -1. Now, some places they will write it kind of with a hat to signify that this is the imaginary number I, but I is the square root of -1. And that's what we're going to be looking at. So the other day when we were graphing the quadratics, where we said the answer for it when it didn't cross the x-axis was no real number, is because the answer actually had I with it, because I, square root of -1, is not a real number. There's no real number that deals with this. But we can still find the answer. The answer is just going to contain I, these imaginary numbers. And imaginary numbers do show up in a lot of different places because, again, electronics, or if you go into electrical engineering, Any kind of computer circuit, diagram, anything with electricity, we have mathematical equations to define it that work with any type of circuit or any type of circuitry. And we can do anything with that, yes? But for anything that we have, so this calculator here is turned off. Is there any electricity flowing through it if it's off? Well, no. I mean, it's off. There's nothing working. There's nothing running it. There is the potential for energy to flow through the circuits, yes? Right. But through the overall circuit board, there's nothing running through the entire system. But there is the potential for it to run, yes? In that moment between it being off and not running, there's not a completed circuit for electricity to run through the entire system. It's what we call the complex plane. It's in mathematically complex numbers for that setup while it's off. Or if you think of a diode that's either on or off, when it's off, it essentially has a complex value, an imaginary value, until it's turned on where it actually has a real value. So it's switching between these imaginary and real numbers, and that's where it shows up a lot of different places. So there's places where this shows up because it gives us a way to define these answers, these non-real values that we can actually have mathematically. We can have a way to equate it, to use it. Yes, sir.
I was going to ask you a question. Did you know that like where you turn off your TV, that's actually there's still power being used when your TV turns off?
The capacitors in the TV are still holding an electrical charge. The circuit itself is not working. So there's not electricity actually flowing through it until you turn it on, which closes the circuit. So the same way as if you're jumping a car, because if you put negative to negative, you can touch the positive ends next to each other all day long. Nothing's going to happen because the circuit is not closed. You can touch the positive to one side, but as soon as that other positive hits something, you've closed the circuit, electricity's flowing. But if you end up just leaving that off, the other positive end off, and it hangs and nothing touches, the other car will never start because there's no circuit closed, there's no actual flow. So that's part of the reason. Now, with those capacitors, the reason they tell you don't mess with them is because as soon as you touch it, you've completed the circuit and it discharges the electricity that way. Does that make sense? Yeah, so even with these calculators or any type of electronics, there is power there. It's going from the power source to that spot. But until the circuit's completed, it's turned on, there is no electricity technically flowing through it. There's some spots that it will, but for the whole, it doesn't, if that makes sense. And that's getting deeper into circuitry and circuits. Any other questions on this here? Now, for us, the first thing we're going to look at is simplifying these here. So the square root of negative 25, we can plug it into the yellow calculator and try to see if it'll simplify it for us. And it's going to give us domain error or non-real answers, because we can take second square root, negative 25, non-real answer. Because again, as we already saw with the first one, negative 5 times negative 5 is not negative 25. What did we say? I is the square root of negative 1, yes? So if we look at the square root of negative 25, that's almost the same as saying negative 1 times 25. Well, we can split that apart and say that we have negative 1 times square root of negative 1 times square root of 25. Well, we know what the square root of 25 is. It is 5. And what have we defined the square root of negative 1 as? Square root of negative 1 is I. So the square root of negative 25 is 5i. Because whenever we have a negative inside a square root, it's going to come out as I. Whenever we have a negative inside the square root, it's going to come out as I. So let's look at the next one. Well, any questions on this first one here?
Wait,
So, so negative 25, we can split it up as negative 1 times 25, which is the same as the square root of negative 1 times the square root of 25. Well, the square root of 25 is 5. Square root of negative 1 is I. So anytime we have that negative inside the square root, it's going to come out as I. Now for the next one, we have square root of negative 72, yes? We can go through that same process we did with the first one. But what do we know? That negative is going to come out as I. So really what we have here is I times the square root of 72. Because we can split it up like that there. Now the yellow calculator, our TI-30XS, will simplify the square root of 72 for us, and we can plug that in. So this here is 6 square root of 2. It'll simplify it for us into radical form. But again, what do we still have with it? So it is 6I square root of 2. Because again, we pull that I out so that the yellow calculator will simplify the radical. Because if we did that by hand, so for 72, we're looking for perfect squares. So 36 times 2 is 72. Because that'd be 36 times 2 is our here. Square root of 36 is 6. We can't take the square root of 2, so it stays. But the yellow calculators will simplify radicals for us. We just had to get rid of that negative so that it could do it. Questions on this here? Let's look at this one here. Negative 5 times the square root of negative 9. Well, we know that this negative is going to come out as I, which leaves us with negative 5 times the square root of 9. Guys, give it back. Now, we could plug negative 5 times the square root of 9 into the yellow calculator, because it'll simplify it for us. Well, the square root of 9 is 3. Negative 5 times 3 is 15, and we have I.
What year was your high school graduation?
2010.
Oh, crap. I thought it was going to be
You guys planning to play again?
old. I just thought it was going to be like, well, actually, I thought it was going to be younger than that. So like 13 or something. But they only got
Everybody 22.
Yes.
I was in elementary.
Questions on any of this here? Now, so guys, we can pull up the graphing calculator. So it gave us an error here, yes?
Yes.
If you notice up next to where it says degree, it says real, yes? That's not on the 30XS. It doesn't say real. Now, guys, if we go into mode, after sequential, you see real, and right next to it is A plus BI, yes? If we go into mode and turn this on, second quit. Now, the last one we had was what? Negative 5, second square root of negative 9, yes? And what is the answer that we found? It was negative 15I, yes? So this here, we can go mode, and down where it says real, we can switch it to A plus BI, A plus BI. And what it's telling the calculator is to look for non-real answers for these complex solutions. So you can hit mode and then scroll down. So with the arrows.
Right there.
Yep, enter. Second quit. Now, there is one thing with this. Second square root, because the other one we had was negative 72, yes? Did that give us the same answer? I mean, technically it did, but we want to leave it in radical form. The graphing calculator is going to convert everything into decimal form. It won't do radicals. So if it works out that it is a perfect square like 9 is, the graphing calculator will do it just fine. But if it's not, it's going to give us a decimal, so we'll end up having to use the yellow calculator anyways. So for the most part, for simplifying these radicals, it's almost easier to just pull the I out, the negative out as I, and plug it into the yellow calculator. So if we looked at these next few here, so negative, square root of negative 4. Well, we know the negative comes out as I, yes? Square root of 4 is 2. So we get 2I. Yeah. Because we pulled the negative out, which is I, yes? But we're wanting to now try to find the square root of 12. We're looking for a number that times itself is 12. Well, 6 and 6 is 36. So this one here is not a perfect square. We can plug it into the yellow calculator, which is, that's pretty high. It is 2I square root of 3. And the reason we get 2 is because 4 times 3 is 12. Square root of 4 is 2. 3 is left inside. But the yellow calculator will simplify the square root of 12 for us. Any questions on 1 or 2? Let's look at number 3, negative square root of negative 36. Well, we know the negative inside is going to be, which leaves us with negative square root of 36. Well, square root of 36 is, so we would have negative 6 I. Because we pull the negative out as I, simplify what we have left, plug I back in. Questions on this here? So the last one we have is 2 times the square root of negative 54. Well, we know for certain our answer is going to have I, yes? Now the part that we need to simplify is the 2 square root of 54. And again, that 30xs, we can do 2 square root of 54, hit enter, and let it calculate it for us. So 6 squared of 6 is our answer, which will tell us that it's 6I square root of 6. Questions on this here? Any questions on any of this here, guys? Questions on anything we've done so far? Okay. Powers of I. Now, guys, again, what we said is I is what? The square root of negative 1. So if we have powers, because again, we can talk about powers of I. I can have an exponent greater than 1. It could be 2, 3, 5, 7, 9. But if I said I squared, we can't leave it as this. We can't leave it with an exponent greater than 1. Because really what we're saying with this here is that I have the square root of negative 1 squared. This would be the equivalent of saying that my answer is the square root of 36 squared. That's simplifiable, yes? Because it works out to be what? 36. Here, well, the square root and square would cancel, telling us that it is negative 1. And we could work through this, going I cubed, I to the 4th, I to the 5th, and going on and on and on. But what it works out is that there's only 4 values of I. It's either going to be I, negative 1, negative I, or 1. These are our only 4 values of I that we have. I, negative 1, and 1. And they go actually in this order. I, negative I, and 1. So we have I, negative 1, negative I, and 1. These are the only 4 values that we can have. And there's an interesting way that this works. Because we only have these 4 values, what we can do is we can take I to any power, if we're given I to a power. Or we're just going to signify that power is in. I to any power. We can take whatever that exponent is and divide it by 4, because there's only 4 options that we can have for I. Only 4 options that we can have. Now, whenever we divide it, we're going to get possibly some whole number, point, and a decimal. Because when you divide by 4, there's only 4 decimal numbers that you can get. 0.00, 0.25, 0.5, or 0.75. That's just how quarters work. Now, if you get a decimal of 0.25, this I to the n is going to reduce to I. If you get a decimal of 0.50, you're going to get -1. If you get a decimal of 0.75, it's going to reduce to -I. And if you get a decimal of 0.00, it's going to reduce to 1. It doesn't matter what the whole number is. We just care about the decimal. Questions on this so far? Okay. So, if we look at reducing these powers, evaluating it, now we could go through and multiply -1 by itself 27 times to see what we get this here. Or, what we can do is take 27 and divide it by 4. We can take 27 and divide it by 4. Because there's only 4 answers that we can get. So we get this here. Now 27 divided by 4 is going to be 6.75. Now we don't care about the 6. We just want the decimal. And 0.75. So when we evaluate I to the 27th, we get -I. Because we can't leave I with any power greater than 1. And that's it. Questions on this here? So let's look at the next one, I to the 34th. So we're taking 34 and dividing it by 4. And 34 divided by 4 is going to give us some number point, what? 5. And we get a decimal of 0.5, the answer is -1. Because again, when we reduce these powers of I, we're only going to have one of 4 answers. It's either going to be I, -1, -I, or 1. And we do the same thing with the next one, 47. So this here is going to give us some number 0.75, yes, guys? Now we could try this in the calculator, because down where the decimal is at, we do have I. And for this next one here, we're taking I to the 65th power, yes? And it is I. What we could have done is taken 65 divided by 4, guys. 65 divided by 4, which gives us 16.25. And our 0.25 responds to I. Yes, sir.
What'd you click to get the I right there?
Second in our decimal. So the answer is I. Because again, the decimal is going to correspond to which of the 4 that we have. So we could do the same thing for the last one, 10, 40. So we can go second I to the 10, 40. Now it gave us this here. Now the 1 plus 4, e to the negative 12 is just saying 4 is multiplied by 10 to the negative 12 I. Because that e to the negative 12, that's what it's telling us, is times 10 to the negative 12. So if we wrote this out, we'd have 1 plus 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. What is this number 0.00, all these zeros for, really close to? So really what this is telling us is that this whole value is 0, which just leaves us with 1. Now if we did it the other way, because 1040 divided by 4 is 260, does it have a decimal? No, so it's understood to be 0, which means this here is 1. Yes, sir. Yes, but I need your card.
You're a funny guy.
You didn't give this to me last week.
I forgot all about it. Thank you.
So it's just 1. Questions on any of this here? Now we can also add and subtract these numbers. Add and subtract these complex numbers, because any complex number comes in the form of a plus bi, where a is the real number and bi is our imaginary number. And we call this overall number a complex number. Whenever we add or subtract, we add the real parts, add or subtract the real parts, and add or subtract the imaginary parts. So let's go on and look at an example of this here, because it's going to make more sense after we work with 1 or 2. So if we look at this first part, 8 minus I plus 5 plus 4I. Now there's not a sign in front of either one of these here, so I can drop the parentheses because we're not having to distribute a negative. So we have this here. Now the real parts, the parts without I, are 8 and 5, yes? So we're going to add those together. We're going to say 8 plus 5. Then we can add the imaginary parts. 4I minus I. What is 8 plus 5? 4I minus I. 4 minus 1 is positive 3. It's negative, it's the square root of negative 1. I is still just the square root of negative 1. But when we're adding and subtracting these here, we can almost treat it like a variable. Questions on this here?
So as soon as we get used to it, we want to write everything.
Because we're doing 8 plus 5. Negative I plus 4I. Now let's look at this one here. Because we have 7 minus 6I. But this minus is going to be applied to both. So we don't have positive 3, we actually have negative 3. Because whenever we subtract, we have to apply that sign to everything after it in those set of parentheses. So the negative 6I is actually going to be plus 6I. Because we have to distribute that negative through. Now our real terms are our 7 and negative 3. 7 minus 3 is? Our imaginary terms are negative 6I and 6I. And what is negative 6I plus 6I? 0. 0I, well, it's just 0. So our answer is 4. Because they cancel each other out. Questions on this here? So we have 13 minus 2 plus 7i plus 5, yes? Now there's an I button on the graphing calculator, isn't there? 13 minus 2, what was it, plus 7i? Is what we had, yes? Minus 2i.
So we could just use the calculator.
11 minus 2i, because if we look back at this, again, we would distribute the negative through, which would be 13 minus 2 minus 7i plus, well, 13 minus 2 is 11. Negative 7 plus 5, 5 minus 7 is negative 2, and we have the I. So we have 11 minus 2i. And that's it. Questions on this here? Do we need to see another example of addition or subtraction? We feel good with these here? Because 2, 9i, 11, negative I. 2 plus 9i plus 11 minus, was it I? 13 plus 8i. Because 2 plus 11 is 13. 9 minus 1 is 8. We get our answer here. Questions on addition or subtraction? Well, the next thing we have is we can. But all we're doing with this here is the same thing we would if we're talking about I as a variable. Because we can do 4i times negative 6. Well, 4 times negative 6 is negative 24. And we have our I. 4i times I is going to be plus 4i squared. But again, we can't leave I with an exponent greater than 1. I squared is negative 1. Because we talked about that a little bit ago. I squared is negative 1. And 4 times negative 1 is going to be minus. We'll want to keep the real term, the number without I, first, and put the number with I second. And we get this here. Questions with any of this so far? We ready for the next one? 15i times negative 1 plus 2i. 15i times negative 1 plus 2i. So this isn't any different than what we've done before. We just can't have I to a power greater than 1. Because we can distribute this here, which would tell us that we have negative 15i plus 30i squared. But again, I squared is negative 1, telling us that we have negative 30 minus 15i. Any questions on any of this here? Are we ready for the next one? Well, 9 minus 2i times negative 4 plus 7i. Again, just like we've been doing with x, we can distribute this. So we can say 9 times negative 4 is negative 36. I times 7i is going to be plus 63i. Negative 2i times negative 4. Negative 2 times negative 4 is going to be plus 8i. And lastly, negative 2i times 7i is going to be negative 14i squared. Well, we can combine these middle two terms. 36 plus 8 is going to be 71i. Now again, I can't leave this as I squared, because I squared is just negative 1. Because negative 14 times negative 1 is going to be positive 14. Which is going to give us negative 22 plus 71i. And again, just like with the ones we did on the previous one, we can type this into the calculator. Nine minus 2i, negative 4 plus 7i. Parentheses 9 minus 2i times negative 4 plus, I believe it was 7i, yes? Gives us the exact same thing. Any other questions on this here? So multiplication, doing this here is almost the same like if I was a variable, I was x. The only stipulation is that I cannot have a power greater than 1. So we have to simplify. Otherwise, it's the exact same as if I was a variable. Questions on this here? So your homework assignment for this here is on page 131. Problems 6 through 12, 19 through 23, 32, 34, and 44 through 50 even. No, just those last few. So 6 through 12, nope, all. 19 through 23, all. 32, 34, and 44 through 50 even. So the only thing we have left to do with 3, 4 with operation-wise is division. It's the only thing we haven't done yet. And we will look at dividing tomorrow.